All right, guys. So today is Monday the 25th, 2022. And this is the video for kind of some notes and our 7.1 synthesis reaction lab. So we started off the day with a warm-up question, and it is about making sure we can identify the number of atoms in a molecule. Okay, so if you were here last week, you remember we use our subscript to help us identify the number of atoms that we have. Oops, and this is supposed to be a subscript 2. Bingo. So in this case, if you remember, we'd have 3 magnesiums, because it says there. Now, with phosphate, again, that's a phosphorus atom with 4 oxygen atoms. And we have 2 of those. So we kind of got to distribute this 2 to all of the atoms in here. So that would mean we have 2 phosphates and we have 8 oxygen, okay? Now, this is going to be really important because a lot of this lab is going to be answering the question or sticking to the idea that matter can't be just created or destroyed. We can't just gain matter. We can't just lose matter without keeping track of it. Okay, and so one way we were going to do that is with a chemical equation. So, how did we write a chemical equation for hydrogen gas and oxygen gas coming together to form water? So if we think back, I'll write it over here. We going into the equation, we call that our reactants. Okay, so we have H2, and we show them that they're going to react by doing a plus sign, just like in math. Our other reactant is oxygen. That's supposed to be an O. So what we have here on this reactant side is our hydrogen gas plus oxygen gas is going to give us, or our yield is going to be water. Now, again, you notice I used an arrow because that's showing the direction that the reaction is taking place. We're going from hydrogen gas and oxygen gas into water. Okay, we're not going the other direction. So again, chemical equations, like we see here, represent a chemical reaction. So if we react these two things together, we can get water. Now, going back to that idea, matter can't be created or destroyed, what we notice is over here, if we count up our atoms, we got 2 hydrogen atoms here, okay? And whoa, that's a circle. And we have 2 over here. But what do we notice here? We have 2 oxygens and only 1 oxygen over on our product side. And so now it's like, well, what happened? We can't just destroy matter. We can't lose one of these. That's where balancing comes into play. So we're gonna look at balancing probably on Wednesday. But to balance this equation, we use what we call coefficients, which we learned about on Friday. And so we'd say, okay, well, I need 2 water molecules, which now gives me a total of 2 oxygens. But now I have 4 hydrogens, so I have to do the same thing over here, and I'd put a coefficient of 2. So you can see total I have 2 sets of hydrogen gas, giving me a total of 4 hydrogen atoms, 2 oxygens on this side, and then again 4 hydrogens and 2 oxygens. We'll practice that more. We'll talk about the rules for balancing equations, but we want to keep in mind this idea that matter can't be created or destroyed. We got to keep track of it. So our first, oops, you can see this more clearly here. So if you need to pause the video and add this, you can. But you can see that we keep track of the number of hydrogen molecules or hydrogen gas molecules that we have. And that's indicated that we have 2 of them, okay? So you can see this a little more clearly. So now, 7.1 lab is about a synthesis reaction. So what is a synthesis reaction? Synthesis reaction is simply a reaction when 2 or more chemical substances combine to form one more complex product, meaning we have A, we have B, and they come together to form AB, just like we showed with our water, right? So we have A, hydrogen, plus B, oxygen, gives us H2O, more complex AB. So go ahead and pause the video and add that to your notes, okay? So with the 7.1 lab, what we did is we are going to be taking steel wool, it's all fluffed up and nice, and aluminum foil. This is more just our pan, but we're going to ignite the aluminum foil. We want to record what happens to the change in mass because we want to be able to account for that difference, right? What happened to that mass? How did we see this change? Okay, and that gets back to matter can't be created or destroyed. So, first thing, make sure again you have your title, your name, purpose statement. So in this lab, we'll be able to predict the outcome of a synthesis reaction. And then we'll be able to complete balance a chemical equation for a synthesis reaction. So our hypothesis then. So we're concerned with mass. Okay, so what's going to happen to the mass? So our hypothesis should read something like, if we burn the steel wool, then the mass will, three options, increase, decrease, or stay the same. Okay, because why ever you think that. Okay, so go ahead and pause the video, go ahead and write your hypothesis. What do you think is going to happen when we light this steel wool on fire? What's going to happen to the mass? Is it going to go up, go down, or stay the same? Okay. Materials, like I said, got steel wool, aluminum foil, and we got a digital scale here. Wood splint, things like that, we're not going to use that. We're going to be pretty fancy, and we're going to use a battery. Okay. So now, our data table. What we have here is we have the mass of our aluminum foil, okay, and then we get the mass of the steel wool. Now, the reason why we have this here is when we burn this, we're not going to be able to take that steel wool and put it back on the triple beam balance. It's going to get all goofed up. So we want to have the mass of our aluminum foil because that's going to allow us to separate it and subtract it from the total mass, just leaving us the mass of our steel wool. Okay, so we'll start with that. We'll go through, see if I can get some good camera views here. So we have exactly 1 gram of aluminum foil. So we can go ahead and put that into our notes. Okay, and then when I add my steel wool to it, it goes up to, I don't know if you can see that, but 7.2 grams. Okay, so to get the mass of my steel wool before we burn it, I take 7.2 minus the mass of my aluminum pan, giving me 6.2 grams. Okay, all right, so once we're there, now we're ready to go. Okay, we're ready to ignite this, and then we'll be able to see the difference. Okay, let's see if we can get a good camera view here. Okay, and we'll use our battery. If you're a survival expert out in the wilderness, you can use batteries and steel wool to start fire. So let's go like this. Get it kind of going here. Oh yeah. Oh yeah. Come on, baby. There we go. How neat is that? Okay. Wow. All right. So almost done there. We can see one final little spark. And we notice now our final mass, 8.4. And again, we have to subtract that 1 gram, but that puts the mass of our steel wool now at 7.4 grams. Okay, so you astute, smart students out there, notice like, what the heck? How did we gain mass? We gained 1.2 grams. We gained 1.2 grams of mass. Okay, so where did that come from? Why did this happen? Okay, so that's what we want to look at. And again, keep in mind, we're learning about synthesis reactions and this idea of conservation of mass. Okay, so first question here. Okay, so in our analysis, sorry. Did our steel wool's mass change? Well, yeah, it went up, which is weird. Okay, so what is steel wool made of? What metal? So a lot of people find on the internet when you Google it's low carbon steel. Low carbon steel. Well, steel is it's an alloy with a mix of iron, which we know now is Fe. We're going to say Fe3, and then a little bit of carbon. Okay, so we're mainly concerned with this. So now, this next question says, think about 3 things you need to start a fire. use those to write a chemical equation, okay? I'm going to go ahead and move us to the board, so this will be a little bit easier. But when we think about a fire, the things that we need are, we need fuel, we need oxygen, and we need heat, okay? And so our battery provides us heat, oxygen's just oxygen, and so now that leaves just the iron as our fuel. So how does this work? How are we going to use this to write a chemical equation? So we know we have iron, right? And well, what did we add to it? Well, we added oxygen. Okay. And now, what is that going to give us? Well, let's apply what we learned from the last unit. Let's write our chemical formula for these. So if we put those two together, we know Fe has an oxidation number of +3 from our Roman numeral. Oxygen's in group 6, meaning it wants to gain 2 electrons, so it has a -2 charge. Crisscross our oxidation numbers, and that's going to give us Fe2O3. Okay, so there is now our chemical equation for this chemical reaction. Okay, so now let's think about this. Next part, it says, onto our synthesis. Okay, we know our mass changed. Where did that extra mass come from? Okay, how did we get that extra 1.2 grams? Well, when we look at our chemical formula or our chemical equation, it becomes pretty simple, right? When we measured the mass of the steel wool at 6.2 grams, that was this, right? We weren't able to measure the mass of the oxygen in the atmosphere, right? Because it's not going to be picked up by our little digital scale. However, when we combine those two, when we added that oxygen and bonded it to the iron, we ended up with our 7.4 grams, okay? From here, we can really just kind of put it as a simple math equation. Well, where did we get that difference? We added 1.2 grams worth of oxygen to our iron. Okay, so that additional mass came from oxygen, because oxygen, it's still an atom, still has mass. So it'll show up when we bond it to that iron. Okay, so now the last question, according to the law of conservation of mass, why is it necessary to balance a chemical equation? Well, when we look up here, we have one iron atom. Let me get these out of the way so we can see this. On this side, on our reactant side, and we have 2 irons on our product, 2 over here, 2 over here. So this isn't balanced. So basically, by balancing chemical equations, we show that we have the same amount of matter going into the chemical reaction as we do coming out. So in this case, we would need to have 4 iron atoms, you'll see why in a second, 3 oxygen molecules, which then is going to give us a total of 2 iron oxides. Okay, so now it's balanced. If we added up all those, it satisfies that law of conservation of mass. Okay, so use that to answer those questions on there, and make sure you take a picture and submit it on Google Classroom when you are done. Thank you.